Hello friends, and welcome to lecture 11 of this open course on diffusion in multi-component solids. In this lecture, we will make a transition from thermodynamics to diffusion. We will understand that chemical potential gradient is a driving force for diffusion, but concentration gradients are practically easier to work with. Various units used for concentrations are also discussed in this lecture. Now that we have gone through a little bit of thermodynamics, we will move on to studying diffusion, in which we will keep referring back to many of these thermodynamic concepts. So, in thermodynamics we saw it helps us to define the state of equilibrium, right, that is the state at constant temperature and pressure, the state at which the Gibbs free energy is minimized. Okay. Now, there can be many equilibrium state, but the state that has the lowest Gibbs free energy or having the global minimum in the Gibbs free energy is the stable state. So, if a system exists in an unstable state, thermodynamics states that it should transform to a stable state, right. So, for example, if we plot the Gibbs free energy of a system as it continuously moves through different atomic arrangements, so we may get a plot schematically which might look something like this, right. So, now there are two equilibrium states, it is called state 1 and state 2, which have minimum in the Gibbs free energy, but state 2 is characterized by the what we call as global minimum, that is the Gibbs free energy of state 2 is the lowest of all other states, and so this is the stable state. State 1, which is characterized by the local minimum in Gibbs free energy, is referred to as metastable state. So, by any chance if we retain the system in state 1, then the thermodynamics says the system should move from state 1 to state 2 spontaneously. Spontaneously here means irreversibly. Remember, spontaneously does not talk anything about the speed of the process, it does not mean fast or slow, whatever. It only says it should move, thermodynamics only says this system should move from state 1 to state 2. Now, since you see the state 2 has a lower Gibbs free energy than state 1, there is a decrease in Gibbs free energy, and that is why the process is irreversible. The transformation from state 1 to state 2 is irreversible, and the difference between the Gibbs free energy of the two states is called the driving force for this transformation. So, there is certainly a driving force for the system to transform from state 1 to state 2. However, you will notice that while going from 1 to 2, the system has to cross this hump. It actually represents a barrier to the transformation, energy barrier to the transformation. That means, before the system can move from 1 to 2, it has to gain certain amount of energy, which is equal to the difference between this maximum in the Gibbs free energy, which is called as an activated state, let us denote it by state A. So, the difference between state A and state 1 is basically the activation energy for transformation. So, until and unless system gains this activation energy, it will not be able to move from state 1 to state 2, and the speed of the process depends upon this activation energy, and this is now in the realm of kinetics. to determine the rate of the process. In this particular case, the rate is proportional to exponential minus delta GA by RT. In the simple theory of kinetics, the rate is proportional to exponential of minus delta GA by RT, where delta GA represents the energy barrier or activation energy. Or we can write rate is equal to some constant k prime exponential. Now, delta GA can be written as delta HA minus T delta SA, where delta HA is the enthalpy of activation and delta SA is the entropy of activation. So, we can write this as delta SA by R times exponential minus delta HA by RT. So, usually these temperature independent terms are combined, and we can write rate is equal to K0 exponential, and the activation enthalpy is usually denoted by EA. So, exponential minus EA by RT. So, you can see the rate of the transformation is basically dependent upon the energy barrier that the system has to cross, and it varies exponentially. So, the rate varies exponentially with temperature. Now, how does the system cross this energy barrier? Yes. So, usually it is assisted by the thermal migration of the atoms, and so these processes are usually referred to as thermally activated processes. Even diffusion is a thermally activated process, right, and that is why you will see the diffusivity follows this relation, d equal to d0 exponential minus EA by RT. So, let us try to see physically the nature of this activation barrier when we talk about diffusion. Particularly, let us take an example of diffusion in solid. So, it is said that the unit step of diffusion in solid is a single atomic jump. So, what is that atomic jump? So, let us consider a simple two dimensional arrangement of atoms. Okay. Let us consider these two sites, call it site 1 and site 2. So, we know that in solids the atoms are sitting in a potential energy well at their equilibrium lattice sites, which means these equilibrium positions are basically the minimum in energy. So, if we talk about this row, this is how the energy will vary with distance, right. So, the atoms are situated at the minimum or in the potential energy well. So, now if this atom has to move on to this site, that is from site 1 to site 2, we see that while doing that it crosses a position which has a maximum in the energy, right. So, somewhere when atom is in between here, it is associated with the maximum in the energy, and once the atom crosses this, then it will fall into the next potential energy well or into the next lattice site. So, this is one atomic jump. For this jump to happen, obviously the atom has to cross this energy barrier. And what is the physical significance of this? What does this physically mean? You can see these atoms are actually touching each other, right. So, when the atom is jumping from this side to this side, when it is in between at the right at the center here, it has to push other atoms apart, and so there has to be an energy provided for that, and that is this activation energy for diffusion. Specifically, this is the activation energy for migration. Now, you can see just having the enough activation energy for migration is not enough, right. The second condition is that the next site also has to be vacant. So, in diffusivity, in this activation energy term, there will also be a contribution from enthalpy of vacancy formation. So, that we will see in detail later, but right now it is just sufficient to understand how this activation barrier is created for this atomic jump. So, now these atoms are continuously vibrating at any temperature above 0 Kelvin, and each vibration does not have the same energy, that is the energy distribution is continuously changing among the particle, and if you consider any one particle or any one atom, every vibration is with different energy. So, certain vibration may have energy greater than the energy required to cross this barrier, and that can be a potential successful jump, provided the next site is vacant, and that is this energy barrier here, and how this is how the thermal vibrations help the process of diffusion. So, diffusion is also a thermally activated process. Now, suppose the chemical potential was uniform throughout the lattice, right. In that case, this potential energy well depths are same, right. So, when atom jumps from position 1 to position 2, there is no change in Gibbs free energy. That means, there is really no driving force for this jump. But what if the chemical potential on site 2 is lesser than that on site 1? Right. So, what is the chemical potential? Chemical potential we defined as mu I is equal to dou G prime by dou N I. So, this is basically the change, how much increase in Gibbs free energy will be there if we add one atom to this system, or how much decrease in Gibbs free energy is there will be there if we remove one atom from the system, right. So, if we see from site 1, one atom is getting removed during this jump, and site 2 one atom is getting added, right. So, if the chemical potential of site 1 is higher than that on site 2, what is going to happen? The decrease in Gibbs free energy around 1 is going to be more than increase in Gibbs free energy around 2. That means, there will be a net decrease in Gibbs free energy, and so there will be a certain driving force for diffusion to occur. In other words, if we look at this potential energy wells, suppose there is a negative gradient in the chemical potential from, that is the chemical potential is decreasing from left to right, right. That means, it is equivalent to say the potential energy well depths are decreasing from left to right, right. So, the atoms on the right are situated in a deeper potential energy well than those on the left. So, obviously, if you see, the activation energy for the atomic jump from left to right is lower compared to that for the jump from right to left, right. So, at any given instant, the fraction of atoms jumping from left to right will be more than those jumping from right to left, and in effect there will be a net flow of atoms from left to right. And so we say the gradient in chemical potential is the fundamental driving force for diffusion. Okay. So, gradient in chemical potential, that is change in mu I with the distance coordinate x. Now, we know mu I is basically mu I 0 plus R T ln A I, where mu I 0 refers to the chemical potential of I in the standard state, and typically the standard state is the stable state of I, stable state of pure I at the temperature T. So, this most of the time refers to the molar Gibbs free energy of pure I at temperature T. You can select any standard state, in that case it will not be the molar Gibbs free energy of pure I, but you need to consider the chemical potential of I in that state. And AI refers to the thermodynamic activity of I in the solution of that composition. So, if we take the derivative with respect to x, this should be constant, right, and if we consider isothermal process, it should be R T d ln A I by dx. Now, A I we know is equal to gamma I times x I, where gamma I is the activity coefficient and x I is the mole fraction of I. So, we can write this as R T d ln x I dx plus d ln gamma I by dx. And if gamma I is constant, we can simply write d mu I by dx is equal to d ln x I is 1 over x I. So, 1 over x I dx I. So, this will be R T over x I dx I by dx. So, this is basically the gradient in concentration. So, you can see the simplest manifestation of the gradient in chemical potential is the gradient in composition. And this is good for us because it is much more easier to experimentally determine concentration than the chemical potentials, and that is why you will see most of the experimental practical formalisms of diffusion, they are done in terms of concentration gradients. Once you know the diffusion quantities in terms of concentration gradients treated as driving force, you can convert them back into the diffusion quantities when we treat chemical potential as driving force. Now, even when gamma I is not constant, we know the interrelations. So, by knowing the thermodynamic quantities, thermodynamic properties of the system, like the thermodynamic activity coefficients and its relation with the composition, we can convert one set of diffusion parameters into the other. Okay, and that is why we will deal with diffusion as driven by the composition gradients. Later on, when we will deal into the theoretical aspect, we will also treat diffusion down the chemical potential gradient, and we can establish the interrelation between the diffusion quantities determined in one form with those determined in the other form. So, concentration is an important parameter here, and concentration can be expressed in number of units. It can be either in terms of absolute amount of component, for example, number of atoms per unit volume of the alloy, right. So, number of atoms per meter cube, or it can be number of moles of I per meter cube of alloy, or it can be in terms of weight, kg of I per meter cube of alloy, or it can be in terms of relative amount of components. Relative amount of components can be mole fraction, which is nothing but number of moles of I divided by the total number of moles of alloy it is usually referred to as Xi. This is also same as atom fraction. Atom fraction will be number of atoms of I divided by total number of atoms of I, and there is only a factor of Avogadro's number between number of atoms and number of moles, right. And so, the mole fraction is basically same as atom fraction, or it can be weight fraction, that is the kg of I per kg of alloy, this is denoted as Wi, or it can be volume fraction, which is nothing but volume of I per unit volume of alloy, is denoted as phi I. So, we will most of the time use the unit for concentration as number of moles of I per meter cube. It is denoted usually as Ci, or in terms of fractions we will most of the time use mole fraction Xi. Okay. Now, what is the advantage of using these fractions instead of the absolute quantities? Right. So, for any type of fraction, for example, sigma xi should be equal to 1, which means out of n components, if there is an n component system, out of n components only n minus 1 concentration variables are independent, the nth one will be dependent. So, if we consider binary alloy, we need to specify only one mole fraction, because the second one is fixed. In ternary, we need to specify 2 mole fractions, the third one will be fixed or dependent. Okay. So, that is an advantage. So, how do we convert one into the other? Because most of the time when we see the flow of atoms or the fluxes of atoms, we will express those in terms of number of moles, obviously per unit area, per unit time. So, how do we convert them back and forth, right? So, for example, how do we convert Ci to Xi? Right. So, Xi is basically mole of I per mole of alloy, right, and Ci is mole of I per meter cube of alloy. To get to here, we need to multiply by meter cube of alloy and divide by mole of alloy, right. So, this gets cancelled and we get mole fraction. So, basically, and what is this? Meter cube of alloy per mole of alloy is the molar volume of the alloy. So, Ci times Vm gives me Xi. So, if instead of multiplying by meter cube of alloy by mole of alloy to Ci, if I multiply by meter cube of I divided by mole of I, what should I get? So, mole of I divided by meter cube of alloy into meter cube of I divided by mole of I. This will get cancelled. I get meter cube of I per meter cube of alloy. So, this is basically the volume fraction phi I. And what is meter cube of I per mole of I? Partial molar volume. So, we write Ci Vi bar is equal to phi I. So, this is important relation. So, if we take the summation over all n components, sigma Ci Vi bar equal to sigma phi I, and we know sigma phi I is 1. So, if we differentiate both sides, we get Ci dVi bar plus sigma Vi bar dCi equal to 0. Now, this quantity we know is 0 based on Gibbs-Duhem equation, right. So, what we get is sigma Vi bar dCi equal to 0. So, for example, in binary we can write V1 bar dC1 plus V2 bar dC2 equal to 0. So, this is an important relation which we will use later on when we try to develop methodologies for analysis of diffusion and diffusion couples. And there is another point here. This makes that when we analyze the diffusion in terms of concentration gradients, right, only one of the gradient is independent, the other one is dependent, if we know the partial molar volumes. Okay. So, we will stop here for today.